Good afternoon. Welcome back to Drive's lectures. As I mentioned in the last lecture class, we have still three topics left over from induction motors. One is going to deal with the behavior of an induction motor, three-phase induction motor when it is fed by a non-sinusoidal supply. That's what we are going to see today. The other two lectures are primarily going to concentrate upon field-oriented control or vector control and direct torque control, respectively. So let's try to look at what happens to an induction motor when it is fed by a non-sinusoidal supply. I'm sure all of you know that basically how a revolving magnetic field is set up in an induction motor. So what we see in an induction motor is somewhat like this. We are going to have, let us say, A phase winding, which is actually shown as concentrated winding here, but that is not going to be the case. Normally, we are going to have 60-degree phase belt that is occupied by A phase and 60-degree phase belt that is occupied by A dash, which is the return path for the current. Similarly, we will have B phase, which is occupying 120 degrees by space. That is, it is going to be shifted by 120 degrees in actual space, and this is going to be the return path for the B phase. So this is going to be B and this is going to be B dash. And similarly, we are going to have C phase here and C dash here. So this is the way the induction motor stator windings are going to be distributed if we are going to have two-pole configuration. So two-pole three-phase configuration for the rotor, it is going to look somewhat like this. Although we are showing this as a concentrated winding, please be assured that almost for 60 degrees, this is going to occupy this. And similarly, for other 60 degrees, this is A dash is going to occupy this place. Similarly, we are going to have C occupying this much and C dash occupying this much. And similarly, we will have B and B dash occupying 60 degree each. So this is the way it is going to occupy. When we actually write the MMF corresponding to A phase, we are going to have, for example, MMF of A phase. So if I say this is MMF of A phase, assuming that we are circulating a sinusoidal current through the A phase winding, it will be, let us say, IM sine or cosine omega t. That is the way we are going to have the current waveform, where Im is the peak value, and it has to be multiplied by the number of turns. And rather than having 60 degree phase belt, if I am going to have the winding also sinusoidally distributed, what do we mean by the winding is sinusoidally distributed? If I say that this is corresponding to 0 degree, this is corresponding to 180 degree, then we are going to have, if it is cosinusoidally or sinusoidally distributed, I'm going to have the maximum number of windings here. So I can show that as a very, very strong amount of current that is being carried. Right next to that, if I try to see cos of 5 degrees or cos of 10 degrees, that is going to be somewhat lower than this. And if I try to look at cos of 20 degrees, it will be even lower than that. So this is the way the number of turns or number of windings, how it is distributed ideally, this is the way it should have been. Similarly, the return current, I should see again at 180 degree point, cos of 180 is -1. So that should be the maximum amount of number of turns that should be there. So I should show it like a very concentrated amount of coil that is being that is occupying the space. And here I'm going to have something like cos of 170 degrees or cos of 190 degrees, which will be lower than 180 degree. and here it should be even lower. So this is the ideal distribution of winding I should be having. If I assume ideal distribution of winding, MMF is going to be current multiplied by the number of turns, right? This is how we are defining the MMF. So I should write Im cos omega t multiplied by, this has to be multiplied by whatever is the maximum number of turns per phase multiplied by cos theta, where theta is talking about the spatial distribution. So this is theta equal to 0 degree, and this is corresponding to, let us say, theta equal to 40 degrees or something. So we are essentially looking at cosinusoidally distributed winding as per the space distribution. So I can write this as FA corresponding to the basic sinusoidal current, that will be NPH, which is the maximum number of turns per phase, multiplied by Im, multiplied by cos omega t cos theta. Similarly, if I try to look at B phase winding will be occupying the maximum number of turns exactly at 120 degrees. So if this is the point at which the maximum number of turns is existing for A phase, I have to go all the way from here to 120 degrees. So somewhere here will be B phase's maximum number of turns. The same way for C phase, the maximum number of turns will exist somewhere here. This is where the maximum number of turns for C phase will exist. So I should be able to write FB, that is the MMF due to B phase current flowing through B phase winding will be, again, if I assume that the maximum number of turns in A phase, B phase, and C phase, they are all the same, then NPH multiplied by Im cos of omega t minus 2 pi by 3 or 120 degrees and cos of theta minus 2 pi by 3. The same way I'm going to have FC, which is going to be NPH multiplied by Im multiplied by cos of omega t minus 4 pi by 3 or plus 2 pi by 3 and cos of theta plus 2 pi by 3. So this is the way you are going to have your MMF distribution. And as per revolving magnetic field theory, we are going to look at the resultant of all these three. So FA plus FB plus FC is going to be the resultant MMF. This is how we define how we get really the revolving magnetic field. So in this particular case, I have to write NPH Im multiplied by cos omega t cos theta plus cos omega t minus 2 pi by 3 and cos theta minus 2 pi by 3. And the last one that needs to be added is C phase MMF, which is cos of omega t plus 2 pi by 3 multiplied by cos of theta plus 2 pi by 3. So this is going to be the total amount of MMF or resultant MMF. So this is cos, which is corresponding to actually 2 cos will be cos A plus B plus cos A minus B. So if I call this as, for example, A and this as B, that is theta is B and omega t is A, I should be able to write this as cos A plus B and cos A minus B. So those two have to be added. So I should say NPH Im multiplied by cos of omega t plus theta plus cos of omega t minus theta. Of course, you may remember the trigonometric identity, which actually goes on like this: cos of A plus B plus cos of A minus B will be equal to 2 cos A cos B. So we are using this identity, so I should divide this by 2, of course. NPH IM divided by 2 multiplied by cos of omega t plus theta and cos of omega t minus theta. Now let us try to take a look at this. This is going to be corresponding to cos of omega t plus theta and minus 2 pi by 3 and minus 2 pi by 3. When I add, I will get minus 4 pi by 3. And the second term is going to be cos omega t minus 2 pi by 3 minus cos theta minus 2 pi by 3. So minus 2 pi by 3 will get cancelled. So we are going to have cos of omega t minus theta. And for the last term, again, we will have cos of omega t plus theta plus 4 pi by 3, because plus 2 pi by 3 and plus 2 pi by 3, when you add together, it will be 4 pi by 3. And when I subtract one from the other, we are going to have cos of omega t minus theta. Right? Now, these are like cos of omega t plus theta, then omega t plus theta minus 4 pi by 3. I can call this as plus 2 pi by 3 and this will be minus 2 pi by 3. So these three will add up to 0. When you add these three, it should add up to 0. Now, these three can be added up together, due to which we are going to have this as 3 divided by 2 NPH IM multiplied by cos of omega t minus theta. So this essentially says that there will be a revolving magnetic field. So, and it is rotating at a speed of, so you should say d omega divided by dt, rather d theta by dt is going to be omega. So the rotational speed of the revolving magnetic field, that is going to be equal to omega, which is d theta divided by dt. And this particular omega is defined by whatever is your frequency at which we are applying the AC current. That is A phase or B phase or C phase current, because we originally defined the frequency of the current by omega. That's why we wrote this as cos omega t. So the frequency of the current is going to decide at what speed the revolving magnetic field is rotating actually. So this is for a two-pole case. Of course, if it is a four-pole case, for example, because I would like to just emphasize this once again so that we are aware exactly how the windings are wound for a two-pole case, four-pole case, and so on. So if this is going to be A, this is going to be A dash. And again, I'm going to have this as, let us say, A1, and this is going to be A1 dash. So the current is exactly reversing its direction. This is dot and this is cross. So when the mechanical angle is 90 degrees, so this is theta mechanical, but electrically, this is already 180 degrees because it has gone through one half cycle completely, even by coming by 90 degrees as far as the mechanical movement is concerned. But the electrical has gone, for example, if I'm going to talk about this is theta equal to 0 degree. Obviously, I'm going to have this as theta mechanical equal to 90 degrees, because this corresponds to A, whereas this corresponds to A dash. So theta mechanical and theta electrical in this case are related by a factor which is P by 2. So I should say theta mechanical equal to theta electrical divided by P by 2. Spatially, you might have seen the displacement to be only 90 degrees, which is theta mechanical. But electrically, the current has already reversed and it has traversed 180 degrees as far as the current polarity is concerned. So this anyway is true for either 4-pole machine we are talking about. If we are talking about 6-pole, I'm going to have again P by 2, which is actually theta electrical divided by 3 will be equal to theta mechanical. So I'm sure you studied about this in your machines course. So the fundamental assumption that we are making is the fluxes or MMF is sinusoidally distributed or cosinusoidally distributed. And for that, we have to have the current to be sinusoidal or cosinusoidal. And the distribution of the winding also should be sinusoidal or cosinusoidal. But ideally, we can say the winding has to be distributed in sinusoidal or cosinusoidal form, but that's not going to be possible because we really cannot have infinite number of slots in the machine, and we cannot have infinite number of slots occupying exactly the number of turns corresponding to sine 90, then sine 89, sine 88, 87, and so on. That's not going to be possible. So that is the reason why we are going to have this particular theta, which is actually indicating the winding distribution spatially. That also is going to have harmonics. So in all probability, when we have non-sinusoidal distribution of winding, instead of indicating this particular winding distribution by cos theta, we might have to indicate this as summation of some cos theta plus cos phi theta plus cos 7 theta and so on. So we are going to indicate this with the help of some kind of Fourier spectrum. That is the way we can represent the winding distribution, which is non-sinusoidal in nature. Any periodic function can be represented by the Fourier expansion, and that's what we are doing. So corresponding to that, we will have actually corresponding to fundamental, we already said cos of omega t minus theta multiplied by NPH multiplied by IM. If we are talking about cos of phi theta, assuming that the current is still sinusoidal, we will have NPH multiplied by IM cos of omega t minus phi theta. Similarly, corresponding to 7 theta, which is actually indicative of the harmonic distribution in the winding, which is corresponding to the 7th harmonic. So that is going to be NPH multiplied by IM cos of omega t minus 7 theta. Okay. So in this particular case, what is going to happen is, we said that for fundamental, we are going to have omega equal to d theta divided by dt. In this particular case, which is corresponding to the 5th order harmonic as far as the winding distribution is concerned, we are going to have omega divided by 5 equal to d theta divided by dt. So the speed, what is actually visualized by the 5th order harmonic corresponding to winding distribution, that is going to be omega divided by 5. Similarly, omega divided by 7 is going to be d theta by dt. So These are generally known as space harmonics. Space harmonics are normally created by a few things. One is non-sinusoidal distribution of winding. Distribution of winding. The second thing is due to some kind of saturation or near the slot. Like if you look at the teeth, so if I have a slotting somewhat like this, I'm going to have the slot in this particular stator outer periphery somewhat like this. This is one teeth, this is the second teeth, and between the teeth, you are going to have the winding arranged. So the winding is going to come in the slot. So due to the slot and teeth, there will be definitely some non-uniformity in terms of the flux distribution. Near iron, it can saturate, and wherever there is a slot where there is more of air, the flux may not saturate. So it is due to slotting pattern. Due to this, again, we can have non-uniform distribution of the flux, which will cause space harmonics. And another thing is if air gap is non-uniform. This can happen due to aging of the machine, or when the shaft was being fixed, maybe there is some non-uniformity. All those things can cause a non-uniform or non-sinusoidal distribution of the flux. And these are called space harmonics. And because these are related to the basic structure of the machine, the space harmonics are normally dealt with in machine course or machine design course. They are not dealt with normally in drives course. So I just didn't want to leave this out. That is the reason why I just thought I'd make a passing mention of the space harmonics as well. And the space harmonics are the one which are responsible for crawling. Very often you might have heard this phenomena called crawling, where the machine might get into a speed of omega divided by 5 or omega divided by 7, where omega is the synchronous speed. So if the synchronous speed is something like 1500 RPM, the machine might rotate somewhere close to 300 RPM, which is actually omega divided by 5. So that phenomena is generally known as crawling, and the crawling is the result of space harmonics. Now, we are not going to deal with space harmonics anymore in this particular course. What we are going to deal with is mainly the time harmonics. So what we are going to look at is time harmonics. So what do we mean by time harmonics? We already said that voltage source inverter or current source inverter can be used to feed an induction motor. So let us say if it is a current source inverter, I'm going to have A phase current somewhat like this. So let us say this is 0 degree and this is going to be pi radians. This is going to be 2 pi. And we are going to have this as IDC, and this is going to be minus IDC, which is given from the current source. So this is corresponding to A phase current. So similarly, I may have the B phase current, which is exactly 120 degrees shifted. So I will have basically this as the B phase current starting from here, and it should go until this point. And this should go on like this. So this is going to be B phase current. And similarly, I should be able to write, so this is corresponding to 2 pi by 3, right? And we are going to have essentially the same way. This is corresponding to 2 pi. So this is the way we are going to have A phase, B phase, and C phase current. C phase current will be again displaced from the B phase current by again 2 pi by 3. So we are going to have this as the C phase current, which will be somewhat like this. So this is C phase current. So this will be 4 pi by 3. And this is going to correspond to 2 pi. Now, if the currents are square wave currents, or even if we are talking about voltage source inverter, in all probability, we may get a few pulses per half cycle. So I may have the positive half cycle somewhat like this. And I'm going to have the negative half cycle somewhat like this. So this is going to be the negative half cycle. So this is the way I'm going to apply the voltage. So this is how it is going to come up as far as the voltage is concerned. So this is omega t, and we are looking at VA, and from VA, VB will be displaced by 120 degrees, and again VC will be displaced by another 120 degrees. So if we are trying to explain the waveform or show the waveform with the help of Fourier expansion, we will have IA equal to some cos omega t times IM1 and IM2 M3 times cos of 3 omega t, then M5 times cos of 5 omega t, and so on. So I will be able to expand this somewhat like this. Now, if I am looking at similarly IB will have Im cos of omega t minus 2 pi by 3. And I'm going to have Im3 times cos of 3 omega t minus 2 pi by 3. And I will have Im5 cos of 3 omega t, 5 omega t minus 2 pi by 3. So this is how B phase current can be represented, right? And C phase, I should be able to write this as Im cos of, Im cos of omega t plus 2 pi by 3 plus Im3 cos of 3 omega t plus 2 pi by 3 plus Im5 cos of 5 omega t plus 2 pi by 3. Okay, so this is the way it is going to be represented. Now, let me try to now look at the fundamental alone. So if I try to look at fundamental component alone, I'm going to have IA equal to Im cos omega t, which has to be multiplied by the number of terms. And cos omega t cos theta, that's what we will get. Then IB is going to be Im cos omega t minus 2 pi by 3. And IC is going to be Im cos omega t plus 2 pi by 3. Okay, so this will create a revolving magnetic field, we know for sure, and we already said that the revolving magnetic field resultant corresponding to fundamental will be NPH multiplied by Im multiplied by cos of omega t minus theta. This is what we said. Now let us try to take a look at third harmonic. What is going to happen to third harmonic? So in third harmonic, I'm going to have IA equal to Im cos 3 omega t. In fact, I3M or Im3 cos 3 omega t. IB is going to be Im3 multiplied by cos of 3 omega t minus 2 pi by 3. So 3 multiplied by 2 pi by 3, when I multiply, I'll get minus 2 pi. So we are not going to have 2 pi. All the angles are measured as modulo of 2 pi. So I'm going to get again cos 3 omega t here. And IC is also going to be IM3 cos of omega t plus 2 pi by 3 multiplied by 3. So 3 multiplied by 2 pi by 3, that is going to be again 2 pi. So we will have cos of 3 omega t. So all three currents, three-phase currents in the third harmonic, they are going to be cophasal. They are going to be cophasal, which is very similar to the zero sequence component. Zero sequence component, when we talk about symmetrical components, they are all cophasal. A phase, B phase, and C phase, they will be cophasal. So this will not create any revolving field. So in this case, we are not going to get any revolving field. That will not be created at all with third harmonic. Let us try to take a look at fifth harmonic. So let me try to take a look at fifth harmonic. So in fifth harmonic, we are going to have IA5. This is IA3, IB3, IC3. Similarly, IA5, IB5, and IC5. IA5 will be IM cos 5 omega t. Whereas if I try to look at what happens with respect to 5 omega t minus 2 pi by 3, so this will be 5 omega t minus 10 pi by 3. So I'm going to write this as Im cos 5 omega t minus 10 pi by 3. If I try to look at it, 10 pi by 3 will be 2 pi, because 6 pi divided by 3 will be 2 pi plus 4 pi by 3. So I should be able to write this as Im cos 5 omega t minus 4 pi by 3. So on a similar condition, if I try to look at what happens to the fifth harmonic corresponding to C phase, I see phi is going to be cos 5 omega t plus 4 pi by 3. So in this particular case, we are getting in fundamental, if we say omega t minus 2 pi by 3 corresponds to B phase, here it is going to be omega t plus 2 pi by 3 corresponding to B phase. Similarly, if we say omega t plus 2 pi by 3 corresponds to fundamental of C phase, omega t minus 2 pi by 3 will correspond to the fifth harmonic of C phase. So we are going to get a revolving magnetic field in this particular case also, but at 5 times fundamental velocity and in reverse direction, because it is like a negative phase sequence. So this is going to be reverse direction. If I say this is A, B, C phase sequence, this will look as though this corresponds to A, C, B phase sequence, because I'm going to have B phase corresponding to plus 2 pi by 3 and C phase corresponding to minus 2 pi by 3. So this is going to be in reverse direction. So this is actually corresponding to negative sequence. It is very similar to negative sequence. When we talk about symmetrical components, we say zero sequence, negative sequence, and positive sequence. So if I say in general, any 6n minus 1 harmonic which is corresponding to, let us say, n equal to 1, 2, 3, 4, and so on. So if I talk about n equal to 1, it is fifth harmonic. If n equal to 2, this will correspond to 12 minus 1, which is 11th harmonic, and so on. All of them, if you analyze, you will see that they all corresponding to negative sequence or reverse rotating magnetic field. But the speed will be 5 times in fifth harmonic case. If I try to look at seventh harmonic case, so in seventh harmonic, I am going to have IA equal to IM7 cos 7 omega t. And IB will be IM7 cos of 7 times omega t minus 2 pi by 3. And I will have IC equal to IM7 cos of 7 times omega t plus 2 pi by 3. So if you look at this, this is going to be IM7 cos of 7 omega t, and 7 twos are 14. So 14 pi by 3. 12 pi by 3 will correspond to multiples of 2 pi. So this will be 12, that is 14 pi by 3 can be written as 12 pi by 3 plus 2 pi by 3. So we will get 7 omega t plus 2 pi by 3. Sorry, minus 2 pi by 3, because I'm having 7 multiplied by 2 minus 14 pi by 3. So we will have minus 12 pi by 3 and minus 2 pi by 3. Okay, so we are going to have here 7 omega t minus 2 pi by 3. And similar analysis will give you that the C phase correspond to IM7 cos of 7 omega t plus 2 pi by 3. So seventh harmonic current will cause the rotation to take place in positive direction. So it is going to be the same direction as that of the fundamental, but at 7 times synchronous speed. So if the original speed is omega s, synchronous speed is omega s, then this speed is going to be 7 times omega s. So the bottom line is, whenever we are talking about the stator winding of the induction motor fed by a current which is rich in all the harmonic components, we are going to have actually multiple revolving field setup. So if I try to look at stator revolving field that are set up because of harmonic rich current. We are particularly going to have, first of all, fundamental at omega s in positive direction. Then all 6n minus 1, they are all going to set up harmonic field at 6n minus 1 times omega s, but this is going to be in the negative direction. And 6n plus 1 harmonics again are going to set up harmonic revolving fields at 6n plus 1 times omega s, and these are going to be in again positive direction. So we are going to have positive direction field set up at 6n plus 1 speed and fundamental speed, whereas negative revolving magnetic fields are going to be set up at 6n-1 speed. Whereas the triple N harmonics are 3 times the original frequency. Those are generally known as triple N harmonics. These are not going to set up any revolving magnetic field at all. So if I talk about 3 or 9 or 15 and so on, all these things are not going to set up any revolving magnetic field at all. So now that we know how the revolving magnetic fields are set up when we use a harmonic rich current to excite the stator of an induction motor, now we are going to have these are the fields. So we can say 1, which is corresponding to omega s, 5, which is corresponding to minus 5 omega s, and 7, which is corresponding to plus 7 omega s. These are the dominant components that are going to be seen. Of course, 11 and 13 will also be there. 11 will be minus 11 omega s and 13 will be plus 13 omega s and so on. This is what we are going to see. Now, these are stator magnetic field. Now, what is going to happen to the rotor? Rotor will definitely have induced current due to the fundamental. It will have induced current due to fifth harmonic. It will also have induced current due to seventh harmonic field that is set up in the air gap. Now, after all, the rotor, let us say, is rotating. The rotor's velocity or speed is close to omega s, which is approximately equal to omega r. The rotor speed is omega r, that is going to be approximately equal to omega s. So slip corresponding to fundamental. If I try to calculate, it is going to be omega s minus omega r divided by omega s, which we said will be 2% or 3%. Right? That's what we said when we talked about induction motor operation. So it will be less than 5% most of the times. If I try to look at what is the slip corresponding to fifth harmonic, the rotor speed is still close to fundamental. So I'm going to have minus 5 omega s minus omega r divided by minus 5 omega s. Okay. So this is going to be, if I say this is 2% or something like that, so I should say minus 5 omega s minus 0.98 omega s, because the rotor speed will be almost 98% of the original synchronous speed, and divided by minus 5 omega s. So this can be written as approximately 6 divided by 5, approximate. So this is going to be the kind of slip we are going to get, which is 1.2 in this particular case for the fifth harmonic. Similarly, if I try to look at what is the slip corresponding to seventh harmonic, which is S7, that is going to be 7 omega s minus 0.98 omega s divided by 7. So this will be approximately 6 by 7. So this is also very slightly less than 1. It is not, so it is going to be 0.9 or something like that. This is going to be more than 0.9. So all the harmonic slips. Similarly, if I try to look at what is S11, it will be basically 11 plus 1. So I'm going to have basically 12 divided by 11. Similarly, S13 will be equal to 13 will be at the bottom, and 12, 12 will be at the top. So 12 by 30. So all these things are going to be approximately equal to 1. So all the slips are going to be corresponding to the harmonic fluxes, they are all going to be approximately equal to 1. So when I draw the equivalent circuit for the induction motor, which is actually working with harmonic power supply. So let me try to draw the harmonic equivalent circuit for fifth harmonic. So if I try to draw the equivalent circuit corresponding to fifth harmonic, I'm going to have this as R1. Of course, there will be skin effect. So R1 may be slightly higher than what it was for the fundamental component. Then I'm going to have X1, but this has to be multiplied by 5 because it is corresponding to fifth harmonic. The reactance will be 5-fold. Now I'm going to have R2 dash by S. So I should be able to write this as R2 dash divided by S5, which is very, very close to 1. S5 is close to 1. So I can write R2 dash by 1.2 or something like that. And I have to write X2 dash, which is also 5 times X2 dash. And this is going to be the overall equivalent circuit of the induction motor. And we are going to have V5 as the voltage, which is corresponding to fifth harmonic component, which is exciting the induction motor. So in this particular case, if I try to look at what is R1 and R2, both of them are going to be much, much less than n times X1 plus X2 dash. In this particular case, n happens to be 5. So it is going to be much lower than 5 times X1 plus X2 dash. So I should be able to neglect this resistances. So as harmonic equivalent circuit, I can simply draw only one reactance and show that as n times X1 plus X2 dash. And I should be able to draw this as n times, rather Vn as the voltage which is exciting the stator. So this is going to be the overall equivalent circuit, and the current which is distributed here or which is circulating here is going to be In. So I can write the harmonic, nth harmonic current is In equal to Vn divided by n times X1 plus X2 dash. This is going to be the nth harmonic current. And if it is a square wave inverter, for a square wave voltage, if you try to do the harmonic analysis, V1, let us say, is 100%. V5 is going to be 1/5 of V1. V7 will be 1/7 of V1. You can try to do the analysis and find out for a square wave voltage how the harmonic contents are decided. You can do the integration and all and find out. You would see that the fifth harmonic is 1/5 and the seventh harmonic is going to be 1/7 and so on. So in which case, we can write the harmonic current now as V1 divided by n square times X1 plus X2 dash, because V5 is V1 divided by 5 and V7 is V1 divided by 7. So V1 divided by n is approximately Vn. So I'm replacing this Vn by V1 by divided by n. So this becomes V1 divided by n square times X1 plus X2 dash. Now, if I try to calculate the torque, which is the harmonic torque, the harmonic torque is going to be 3I2 square R2 dash divided by S omega S. This is what was the original expression for the torque. So now if I want nth harmonic torque, I should write this is IN square, whatever is the nth harmonic current. And I should say what is R2N. Due to skin effect, it can increase slightly, no doubt. And this is going to be Sn. And this is going to be omega S corresponding to nth harmonic. The synchronous speed corresponding to nth harmonic. Now let me substitute for these values from here. What is IN? Let us substitute. What is slip corresponding to 7th harmonic or 5th harmonic? All of them are close to 1. That's what we said. So in which case I should write 3 multiplied by V1 square divided by n power 4 multiplied by x1 plus x2 dash. And Sn is corresponding to 1 because that is the slip corresponding to any harmonic frequency. This, let us say, is R2 dash itself. It may be slightly increased. Now, synchronous speed is n times omega s, where omega s is the fundamental synchronous speed. So this is going to be 3 V1 square R2 dash divided by n power 5 multiplied by x1 plus x2 dash multiplied by omega s. So compare this with the fundamental component. The fundamental component is going to be 3 V1 square multiplied by R2 dash divided by S1, whatever is the fundamental component of slip. Here it is going to be R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square. And this has to be multiplied by omega S. So first of all, harmonic current itself is going to be very low. And on the top of that, because we are having n power 5 in the denominator, we are not really going to have a good amount of harmonic torque. So we can say, although we might have to calculate this in case we are having a huge amount of harmonic voltages that is being applied to the induction motor. But even for a square wave, we are going to get a harmonic torque which is much, much less than the normal fundamental component of torque. So the conclusion is, even for a square wave voltage, harmonic torque values are negligible. So when we talk about fifth harmonic flux inducing a fifth harmonic current in the rotor and the interaction between the fifth harmonic air gap flux and fifth harmonic rotor current producing a torque, that torque value is going to be negligibly small. Even for fifth harmonic, seventh harmonic, it will be even lesser. 11th and 13th, it will be really much less as compared to even fifth harmonic. Okay. So on the whole, the harmonic torques are not going to pose a major problem for the working of an induction motor. But what is really going to create trouble is, let us say on the stator side, I have flux corresponding to fundamental component, flux corresponding to fifth harmonic, flux corresponding to seventh harmonic. This is rotating in the negative direction, whereas this is rotating in the positive direction. Similarly, I'm going to have flux corresponding to 11th harmonics, which is rotating in the reverse direction, flux corresponding to 13th harmonic, which is rotating in the positive direction. Now, these are going to induce current in the rotor. So, rotor currents, what I would see again, corresponding to fundamental, I will have fundamental rotor current, which is also supposed to be oscillating at a frequency of synchronous frequency when I watch it from outside the machine. As a stationary observer, if I watch it, it will be corresponding to fundamental. So this is going to be I fundamental, which is rotor current. Now, I will have corresponding to these two. That is, fifth harmonic revolving magnetic field is in the opposite direction. So this is fifth harmonic revolving magnetic field. Whereas I'm going to have the rotor rotating in the direction opposite to that of fifth harmonic revolving magnetic field, that will be at omega s. So the corresponding induction that is taking place in the rotor because of the fifth harmonic revolving magnetic field, that will be corresponding to minus phi omega s minus omega r, which is also approximately omega s divided by minus phi omega s. This is slip, but the relative velocity that will be seen, that will be actually approximately 6 times omega s. So what we are going to get as the induced EMF frequency because of reverse rotating fifth harmonic flux and forward rotating seventh harmonic flux, that is going to correspond to sixth harmonic. So this is going to be I26. Similarly, this is going to be corresponding to I2 but 12th harmonic. So this is the sixth harmonic, whereas this is going to be the 12th harmonic. Now with fundamental, if the sixth harmonic current is kind of, interacting, fundamental flux is going to be really large, whereas the sixth harmonic current may be small. Similarly, fundamental flux is large, but the 12th harmonic current may be small. So you may have the current, rotor current to be small, but you are going to have the fundamental flux to be large, because of which we will have the interaction between phi 1 cosine omega t, and we are going to have I26 cosine 6 omega t. So we will have actually 6 omega t minus omega t and 6 omega t plus omega t as two components of torque. So there will be a seventh harmonic torque, and there will be seventh harmonic component of torque, and there will be a fifth harmonic component of torque. So 6 omega t minus omega t and 6 omega t plus omega t. These will be the two components of torque. So this will be fifth 5 omega t component and 7 omega t components of torque. So if you look at the average values of these torques, those will be 0. Because if I try to integrate over 0 to t, it is going to definitely give me 0. Whereas instantaneous values will be non-zero. Instantaneous values are going to be non-zero. So if I say that, for example, I'm going to plot the torque with respect to time. The fundamental component of torque is a steady value. I'm going to have a steady value. Whereas the seventh harmonic torque and fifth harmonic torque, I may have the fifth harmonic torque superposed on this somewhat like this. So I'm going to have 5 times the frequency. So 1, 2, 3, 4, and 5. I'm going to have 5 times the frequency. So this is the fifth harmonic torque. Whereas my seventh harmonic torque may be smaller than this in terms of magnitude, but it will have a higher oscillation frequency. So this will be fifth harmonic torque, whereas this will be seventh harmonic torque. Average value will be 0, no doubt, but we are going to have, if I try to look at it at some point, fifth and seventh and fundamental will add up together, because of which I may have a little bit of positive torque and I may have some amount of negative torque and so on and so forth. So average value will still correspond to the fundamental component of torque, but we may have some kind of oscillations in the torque because of the instantaneous values of fifth harmonic flux interacting with fundamental rotor current, or fifth fundamental flux interacting with fifth or sixth harmonic rotor current, and so on. So these are going to create oscillatory torques. And these oscillatory torques, although they will have average zero value, they will contribute to some amount of oscillations in the overall torque experienced by the shaft. So these will cause the oscillatory torques contributed by instantaneous values of harmonic torques. These are going to cause vibrations or variation in the velocity, variations in the speed. So these are definitely not good for motors which are actually having a few hundreds of kilowatt rating. That is the reason why repeatedly we insist on voltage source inverter or current source inverter. They should work on PWM principle, whose waveform output will actually emulate sinusoidal quantities. So in general, it's not a very good idea to feed large induction motors of hundreds of kilowatt rating with square wave voltages or square wave current. And that is the reason why the input to an induction motor should always emulate, it should always emulate sinusoidal voltage and sinusoidal current. Although the actual harmonic torques, which are created by fifth harmonic voltage interacting with fifth harmonic flux interacting with sixth harmonic or fifth harmonic current, and if you try to look at the seventh harmonic flux interacting with seventh harmonic current, these are going to essentially induce literally negligible torque. Whereas when we talk about oscillatory torque that are due to the interaction between fundamental flux and sixth harmonic current, or sixth harmonic flux with fundamental current, these are going to create oscillations and vibrations in the rotor shaft. And that is definitely not good for a large capacity induction motor. And that is the reason why we generally insist on having either sinusoidal voltage or sinusoidal current when we are feeding an induction motor. Okay, so much so for harmonic fed induction motor, three-phase induction motor drive. We will take a look at field oriented control in the next lecture class.